Hi, I'm Zor. Welcome to Unizor Education. Well, today we will start something which is called Lagrangian. This is a subject of the course Physics Plus for all, presented on unizor.com, and I do suggest you to watch this lecture from website unizor.com, not only because it's totally free and there are no advertisements, you don't really have to even sign in. It's because it's a course, which means there are interrelated lectures presented in certain order when something which I kind of presented before will be used later. Now, in this particular case, within this Physics Plus course, my previous subject was variations, and I'm going to use it for this particular chapter of this course called Lagrangian. Okay, now first of all, let me start from something which is some people kind of don't even think about. In mathematics, you can prove something. So there are certain axioms, then there are some logical conclusions. Based on these axioms, we can derive some theorems, and from these theorems more theorems, etc. Now, in physics, in mechanics, we used to think about laws of Newton. Well, they are basically axioms. I mean, we don't really derive them from anywhere. It's based on our experiment, and we trust them, well, up to a degree, obviously. But if we are talking about Newtonian mechanics, it's all based on these three laws of Newton, and these are purely axiomatic. We just don't prove it. There is nothing we cannot prove it, basically. We take it as granted based on our experience, and from these laws we derive some other theorems, or whatever you want to call it in physics. They're not called theorems actually, but no matter. Now, is it the only way to approach our physical world? These three laws of Newton, they definitely give the good foundation, but in some cases, some problems are very, very difficult to solve using Newtonian mechanics. And I will actually go through these problems later on, maybe in further lectures. But today I would like to introduce just completely different approach, which is basically attributed to Lagrange. That's why it's called Lagrangian. Now, this is approach which is supposed to be equivalent to Newtonian mechanics. So Lagrangian mechanics is basically producing the same results. So if Newtonian mechanics gives you some kind of an equation from which you can start, which is like F is equal to m times a, force is equal to mass times acceleration. Now, what is this? This is actually a differential equation of the second order, because acceleration is the first derivative of speed, and speed is first derivative of position. So as far as the position is concerned, if you know the position, what's the force at that particular position at that particular time, then basically what I can say that F is actually a function of time. Maybe it's function of position of time, but it's still finally function of time. And A is actually a second derivative of position by time. So this is some kind of a second order differential equation. Now, it's based on force, which is the most kind of a unknown thing. I mean, we have to really describe the force to find out, to solve the differential equation and find position as a function of t. Trajectory, basically. The force determines trajectory. Sometimes it's difficult. Now, the Lagrangian approach, although equation looks much more complicated than whatever I was just wrote, F is equal to ma, much more complicated Lagrangian equations, but it actually seems to be easier in many cases, because the forces are much more difficult to determine in many cases. Force is basically a vector in three-dimensional space, and it would be much easier if we would deal with scalars. And that's what Lagrangian actually is all about. Okay. So it's different. Lagrangian mechanic, it's different in their form, in their equations, but it delivers the same result, the same trajectory. Okay, now let's start with a concrete example. So I will just do it with this example to show how Lagrangian can work as well as Newtonian mechanics. So the example is very simple. Let's consider you have a spring with an object at the end. Now, we only consider a very, very simple case. These movements back and forth, forget about the gravitation or anything else. So it's only this force of the spring which is important. So this would be my x-axis. Now, and this would be in a neutral position of the spring. That would be x is equal to 0. Now let's continue basically describing how the movement would be. Now, there is a Hooke's law. Remember Hooke's law? Hooke's law. Now the force is equal to minus kx, well, of t, obviously. K is elasticity of the spring. X is displacement, positive or negative. But in any case, if it's positive, if we are stretching actually the spring, then the force goes to the left, and that's why there is a minus. If my x of t is negative, left to the 0, then the force would be towards positive, so that's why there is a minus. So this is the Hooke's law, and it's equal to mass times acceleration. Well, acceleration is second derivative of time. So this is a differential equation for a simple spring movement, object on the spring. And obviously, if we know elasticity of the spring and mass of this object at the very end, assuming spring is weightless, obviously, we can solve this differential equation. This is some kind of a sinusoidal movement. X would be sinusoidal because the second derivative of sine is basically also sine, and it's also just the game of coefficients. Okay, now I would like to approach it slightly differently. Let's think about two different scalars. That's very important: kinetic energy and potential energy. Now, what's kinetic energy of the spring? Well, it's half mv squared, right? Well, v is the speed, and speed is the first derivative of position, so it's 1/2 mx of t squared. Okay? Now, let me just do everything with kinetic energy. What if we will just make a derivative of kinetic energy by speed? So d kinetic partial derivative. I'm not doing by time, I'm doing just by v. By v. Well, this is mv, right? The derivative of v squared is 2v. 2 and 2 will cancel out, so we have mv, which is basically the momentum. Now, it's quite interesting. I mean, you probably don't think about this, but there are certain connections between certain objects which are, well, maybe strange, maybe unusual, and maybe there is some very deep sense in the fact that they're connected. So, connection between kinetic energy and momentum. The derivative by speed of kinetic energy is momentum. Well, that's how it is. Now, what's another thing interesting, what if I will consider this as a function of time, actually? Now, what if I will differentiate it by time? d per dt of dE kinetic by, instead of v, I will put x prime, which means the derivative of position, which is v. What is it? Well, the derivative of speed is acceleration, right? And this happens to be, according to Newtonian mechanics, the force, right? So we have derived the force from kinetic energy. It's purely artificial. Why do I do it? Well, obviously I know the result which I'm going to, but again, what's important is that we can derive components of the Newtonian mechanics from some other things. Again, F is might be a very complex thing. Sometimes energy, you can approach energy in kind of an easier way. And that's why if you know the energy, kinetic energy in this particular case, maybe in some cases it's easier, instead of just manipulating with components of the force, just have the entire kinetic energy of the object, and basically from this kinetic energy derive all the components of the force, because the force can be a result of the many different forces from different places. Okay, so we have come up to this. Now let me have some space here, and let me start with the potential energy. Potential energy of the spring, potential is equal to 1/2 kx of t squared. Now, I do remember this formula, but again, if you don't, you can always go to any source of information, including Unizor.com. There is a course, Physics for Teens, and there is a chapter called Energy, and within it there are some energy for different objects, including the spring. So it's all explained there, no problem with that. So I'll take it as given. Well, let's do the same thing. Let's do dE potential, in this case by x. What is it? Well, that's obviously by x, not by t, by x. So it's 2x, and 2 and 2 will cancel out, so it will be k times x of t. Which is F is equal to minus k x of t for a spring, right? So which is minus F. Also F. Now this F in this F. And as a result, we have an equation which can be expressed the following way. d by dt of partial derivative of kinetic energy by speed is equal to d per dx of minus E potential. I put minus here, so it will be plus here. This is F and this is F. Okay, now let's think about it a little bit better. You see, kinetic energy is independent of position. It depends only on the speed, right? It's 1/2 mv squared, so it only depends on the speed. Which means if I will, instead of this kinetic energy, I will put E kinetic minus E potential, a potential does not depend on the speed at all. Potential depends on the position, on x of t, right? That would be exactly the same. Similarly, potential energy depends on x, on the position, and it's independent of the speed. Doesn't matter what the speed of the object is, potential energy is the same. So if I will add here kinetic energy, which is independent of position, depends only on speed, that would be the same as well. Well, because d per dx prime of potential energy is 0, and d of kinetic energy by x is also 0. Potential is independent of x prime, and kinetic is independent of x. Which means I have an equation which depends on this particular thing. D by dt, dl by dx prime. I probably should put here L of x of t comma x prime of t. That would be better, right? It's still a function of t, obviously, of time, but we are not directly depending on time. We depend on position and the speed. Kinetic is speed related, and position is potential energy is position related. So I put this of x of t, x prime of t is equal to d by dx of the same L of x of t comma x prime of t. Okay, now for those who remember the previous lecture, which was about variations, they will recognize the equation. This is equation which actually determines trajectory, which minimizes or maximizes some function now. So let me go back to variations, and I will remind you this. Now, if you have a function now, which is a function of function, now this is trajectory. X is argument and f of x is function. So let's say we are going from this point to this point. Okay? Just on the plane, in a very, very simple case. Okay? Now, if this can be expressed as an integral from a to b, a, b, of some real function of 3 arguments, x, f of x, f prime of x, dx. Well, for example, the length of this curve is a function, or the time when some object frictionlessly going along some trajectory f of x from point A to point B, then the time which takes to go from A to B is a function. So if we would like to minimize the value, for example, what is trajectory to minimize the time of descent from A to B, then this particular, the answer to this is solution to a differential equation, and differential equation is called Euler-Lagrange differential equation, and it looks actually very much like this one. df by df prime of x f of x and f prime of x is equal to d by df of f of x, f prime x. So this is Euler-Lagrange equation, which was derived in previous lectures, which were dedicated to variations. That's why I actually put variations inside this Physics Plus course, because it all depends on these Euler-Lagrange equations. Now, the only thing is, this argument is x and the function is f of x. Now, obviously, I can change the argument. Instead of x, I can put time t. T, 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 and instead of x I will put position x. X prime, x, x prime, x, and x prime. So I just replace argument. Instead of x, I put t, and instead of f of x, x of t. I hope you don't confuse this x and this x. This is the function which is replacing f of x, and this x is the same as time. So it's exactly the same equation. Okay, so that's very important. So Euler-Lagrange equation delivers basically the same solution if, as a function f, we will take this one, Lagrangian. So the whole Lagrangian mechanics is based on the fact that if instead of this function in the functional, whatever the functional is, we will use the Lagrangian, which is difference between kinetic and potential energy, and construct the Euler-Lagrange equation, we will get trajectory. We will get a solution to this function x of t is a trajectory. So now let's go back. What is exactly this solution? Solution is minimization or maximization of this functional, right? So what is the functional which related to this Lagrangian? Well, that's obviously a very simple thing to do. It's integral functional of trajectory. It's integral, but now our argument is not a to b of x, it's time t to time 2 of Lagrangian. X of xt, x prime of xt, dt. So again, I have replaced argument with t, which is time, and function with x of t, which is position. So this is the functional. L is this function. It depends on position and speed. Speed is in the kinetic energy, position is in the potential energy. Both are functions of time, of course. And minimization or maximization, extremization, if you wish, of this functional is basically the solution which gives this Euler-Lagrange equation, which gives the trajectory, and this solution is exactly equivalent to approach of Newton. F is equal to ma, because it's also, this is a differential equation of the second order, and the Newton's equation F is equal to ma is also differential equation. So that one, Newton seems to be kind of simpler than this one, but trust me, the problem is in this equation, the problem is this force. because sometimes this force is a combination of many different forces, and to combine them together is not easy because they're all vectors, etc. Here we're dealing with scalars, kinetic energy and potential energy, which might be kind of known from different kind of considerations. And it looks like the more complicated the mechanical problem is, the easier it is to use Lagrangian mechanics than Newtonian mechanics. Now, the last thing which I don't remember, did I say that this is called action? This function now is called action. This one. So action is integral of Lagrangian, and minimizes or maximizing action is trajectory which the object takes based on if we know its kinetic and potential energy at every point. So at every point, if we can determine kinetic and potential energy of the space where this object actually is going to. Now this equation, the Euler-Lagrange equation, gives you the trajectory. Okay, and one more thing, I kind of derived this thing based on spring as a concrete example. Yes, it's a concrete example, but it's basically quite universal, because, well, kinetic energy is always 1/2 of mv squared, right? And as far as potential energy is concerned, think about what is potential energy. Potential energy is very much related to work, right? Like, for example, if we are lifting up a stone at a certain height above the earth, we spend some energy and we do work. And whatever work we do is actually a potential energy which this stone has, right? And work is what? Work is differential of work, minima, some infinitesimal piece of the work which we do. It's the force times times the distance this force is actually acting, right? So the derivative by position is the force. So that's exactly what we had with potential energy of the spring. So that's very important, which means it's basically universal, and Lagrangian mechanics is relatively universal, as I said. So what's important is, first of all, to understand that it's all related to functionals. It relates to theory of calculus of variations, and Euler-Lagrange equation is basically the fundamental tool you use instead of F is equal to ma Newtonian equation. You are using this Euler-Lagrange equation. And again, dependency is on the energy rather than on the force, which in many cases seems to be easier. Well, that's it for today. I would like to again mention that it's better to watch this lecture on Unizor.com. You go to Physics Plus All course. Now, this particular part of the course is called Lagrangian, and today was the first lecture, just introduction into what Lagrangians actually are all about. And again, prerequisites, very important prerequisites. Now, before that there was variations, and before that there was the whole course of physics for teens, where I explain much more simpler aspects of physics. So that's all very important. Now, also very important, together with every lecture, video lecture on Unizor.com, you have the notes for the same lecture, which basically I write notes. It's like a textbook, basically, very detailed notes, and then I will record the lecture when I a little bit kind of refresh my own memory, etc. So it's very important to have both video and notes, because sometimes I'm shortening my video, saying, okay, there are some technical manipulations which are not really very interesting, just pure algebra or something like this, and I refer you to the notes for the same lecture where all these calculations are explicitly made sometimes. Also, the website has exams which you can take anytime you want. Not all the parts of all the courses have exams, but many do. Also, what's important to mention, there is also the math courses. There is a math for teens, and there is math plus, and there are some other interesting aspects on the website, like relativity, for example. There's a special theory of relativity. So I do suggest you to use Unizor.com. If you found this lecture somewhere else, like on YouTube, well, that's fine, but at the same time it's better with Unizor because it doesn't have any commercials, or doesn't interrupt you. It doesn't have any advertisement, and you don't have to log in if you don't want to. I mean, there are some circumstances when you might want to if you are supervising or you are supervised by somebody else. But generally speaking, if you just do it by yourself, you don't even have to sign in. Okay, that's it. Thank you very much, and good luck.